So first thing you need to check the distance between C1 and C2. If it is more than R1 plus R2, that means the circles are far apart, they don't intersect. The other thing is, if this distance is less than absolute of R1 minus R2, that corresponds to the situation when one circle is inside another circle. Again, they don't intersect. If they are just equal to R1 plus R2 or R1 minus R2, that means the circles touch. So R1 plus R2 corresponds to external touch. R1 minus R2, the distance equal to R1 minus R2, corresponds to the case when this circle touches internally to the other circle. In both those cases, it's very easy to find the intersection point, because when you take a straight line, so let's say this, I'll draw it. So you have a center C1, you have a center C2. This point divides this line in ratio R1 is to R2. So you can simply get this point by doing a weighted average on this line. So in case the circles touch, it's very easy to find the intersection point. Is this clear? Now the final case is when the circles actually intersect. The case corresponding to this. So I'll draw it again here. So obviously you can find this point by doing R1 is to R2 on this line, right? But you want to find the intersection points. Note that if this was a perpendicular, this is a perpendicular obviously, so you already know this distance. How do you know this distance? You have this distance and you have the radius. Applying Pythagoras theorem, you will get the distance, after which you will get this point. You also want to know the direction. The direction is simply perpendicular to this direction, this line. So you get a line which passes through this point and is perpendicular to the line joining the centers. So you can go either way, this way, this distance or this distance, and you will get these points. So how to get the pair of points? You will get the direction of this line. Let's say that is vector V. This point, let's say, is point P. The 2 points would be P plus V and P minus V. This V I am assuming have the correct magnitude. That you can simply convert. Is this clear? By applying a little more geometry, you can also solve cases of intersection of a circle with a line or line segment, or drawing tangents of a circle. You just need a bit of geometry, finding out some angles and all, and then it will fall down to one of these problems. So you can solve most of the basic geometry problems without taking a lot of cases using these techniques. There are some other geometry problems which are fairly frequent in programming contests. One is when you want to find out the number of lattice points inside and on the boundary of a polygon. Do you know what a lattice point is? Lattice point is something which has integer coordinates, that's all. So for this there is something known as Pick's theorem. It gives a formula which we use. I am not going to cover it. You guys can just search and look for this Pick's theorem. How it relates the points inside a polygon, points on the boundary of a polygon, and the area of a polygon. It relates these three things. So if you know area and one of the other two, you can get the third one. Is this clear? Just look up this theorem on that. The next thing is, if you want to check if a point is inside a polygon or not. So there are two cases in this problem. If the polygon is convex, it becomes very easy. So you have a convex polygon. Let's say, let's draw a regular hexagon. You have a point. You simply draw a ray from this point to any point on the polygon and extend it either side. If it passes through 2 points, that means this point is inside, and if and if these 2 points are on the other side, that is, right? And if this point was outside somewhere, yeah, essentially, sorry, you can take a ray starting from this point, going in any direction. If this point is inside, it will obviously hit some end of this polygon. If it hits exactly one end, that means this point is inside the polygon. It may be possible that it may not hit any end, like a ray, something like this. That also means the point is outside. And if it touches even number of points, that also means the point is outside. So when there is exactly one intersection, we know that the point is inside the polygon, otherwise no. Intersection, here we are talking about intersection of a ray with a line segment, which again falls into one of these categories which you can solve, right? So this method only works for convex polygons, it won't work for concave polygons. So for concave polygons, you need a slightly advanced method. So if your polygon is something like this, your point is somewhere here, what you try to find out is the sum of angles each side will subtend on this point, like this angle, similarly the third angle and the fourth angle. So the sum of all these angles, if it is equal to 360 degrees, that means the point is inside the polygon, otherwise it's not. Is it clear? To find out each of these angles is very simple. You draw a vector from this point to this, you draw a vector from this point to the other point, and calculate the angle between these two vectors. And also make sure you use the sign, that you use a cross product to find the angle, because here the angle also has a direction associated with it. It's just not an absolute angle, right? So you need to keep track of direction. So you use cross product and then do a sign inverse. So if cross product is negative, that means you add a negative to the angle. Is that clear? So this is what you do for concave polygons, to find whether a point is inside a polygon or not.
So we can still draw to a random point, right?
Yeah, it may not work. It is highly likely that it will work, but it may not work. So for example, if you have point somewhere here, you draw a ray like this, the point is inside, but this ray touches like 3 points or something.
No, I mean if it's odd, if the number of intersections.
Okay, we can take another example. Something like, if the point is here, you draw this line, it passes through a vertex. I mean, there are cases, I could come up with more cases. You can
still keep taking random points still, as long as it doesn't pass through a vertex, it doesn't coincide with the segment.
No, it still won't work. I am not able to come up with a case, but it still won't work. Take my word for it. So you have to use the angle method if the polygon is concave. Yeah, actually this works. I made a mistake, but this you essentially might have to try for some time until you find a ray which doesn't intersect on a vertex. But the other method is simple. You take sum of all the angles. It has to be 360 degree for point to be inside the polygon. Now these are the basic things in 2D geometry. I will cover some more things in 3D geometry, which again can be solved using vector algebra. So a line in 3 dimensions can also be defined by 2 points, and so a line vector would be having 3 components instead of 2, as in 2 dimensions, right? So I'll quickly tell you how to find out line intersection. So if there are 2 lines which are not coplanar, as in one line is in some plane, the other line is in some other plane, then they won't intersect. How to check if 2 lines are coplanar or not, I'll just tell you. And if they are coplanar, then Suppose one line is this, one line is this. So we find out the cross product as we did in 2D case, but this time the cross products would be a vector, but the distances still vary linearly. So we will be able to get a similar formula which we had in 2D case, that is vector C plus vector D minus C into the distance. That is clear? We can similarly solve line segment or rays or whatever in 3D as well. Now let's take a definition of a plane in 3D case. So if we have 3 points which are not collinear, these 3 points can define a plane. So if these 3 points are collinear, they can define a line. If they are not collinear, any 3 points will define a plane. So in this plane, I will have 2 vectors. So essentially how I represent this plane is, I take the cross product of these 2 vectors, that is AB and AC. That cross product is normal to the plane, right? So I will get a normal vector to this plane, and I will have at any one point in this plane that will define the plane. Now suppose if we want to find out if 4 points are on the same plane or not. So we will find out the plane defined by first 3 points. Then let's say fourth point is like somewhere here outside this plane. So you will take that 4th point as, let's say, D. You calculate this distance AD. This is also a vector. You take dot product of this vector with the normal to the plane. So if this vector had any component towards the normal, then the dot product would be non-zero. That means this point is outside the plane. Is this clear? So dot product of AD into AB cross AC. AB cross AC is the normal vector. We take dot product of this with AD vector. If it's non-zero, this point is outside the plane. That means they are not collinear, otherwise they are so in that case they are not coplanar, otherwise they are coplanar. Is this clear? We can also find distance of a point from a plane just by dividing this dot product by magnitude of this vector. Is that clear? Just like we did a distance from a point to a line. If we divide this dot product by magnitude of this normal vector, we will get the distance of point from the plane. Again, in this the vector algebra extends to 3D, but rest of the things remain same. So it's not very hard to generalize from 2 dimensions to 3 dimensions, any problem. Similarly, so I told you about distance of a point from a plane. If we wanted to find reflection of a point, we already have the normal vector to the plane, we have the distance, we will project it twice the distance to get the other point. Just like we did in 2D while finding reflection of a point with respect to a line. The next problem which I will take is, if you want to find out equation of a sphere which passes through given 4 points. You do understand that a sphere cannot be defined by just 3 points, right? In 3 dimensions. So we need 4 points to define a sphere, and those 4 points should not be coplanar. So we will first check if the given 4 points are coplanar or not. If they are coplanar, we cannot solve this problem. If they are not, what we will do is, so suppose we take the plane given by first 3 points. We will find out the point which is equidistant from these 3 points, that is circumcenter of this triangle, right? This we can find by calculating intersection of perpendicular bisectors. We got this point and we get normal vector to this plane, which we have. So we got this point and normal vector. We will do this for any other set of 3 points. So let's say this is ABC, D is somewhere here. We will do for ABC and ABD. We can take any 2 pair of